So that's the first step in counting sort. We're counting how many of each kind there are. So any questions about that before I press on? All right. So I've just copied over my data and my count array. And here's the sorting phase. We just create an empty array that's just the same length as our data array we're trying to sort. And we run backwards through the data array, and we go to the last element of the data array, use that as an index into our count array, decrement that by 1, and then store the 2 at index 4 down here. Let me back up. Why does that work? Yeah?
Because there's that many numbers left too, so you know that's kind of less as well.
Okay. We know there are 5 numbers less than or equal to 2. 1, 2, 3, 4, 5. So the last 2 would go right here. So we decrement the 5 to get the actual index. And put the 2 right there at 4. Then the next time we find a 2, where will it go? I mean, in other words, why do we update the count array? Because the next time we want to stick a 2 in, it needs to go here. Once we sorted that 2 into the right spot, now there are 4 numbers up there less than or equal to 2. And we just sweep to the left. So now we'll go to the left here. There's 7. We go to index 7. So there are 11 numbers less than or equal to 7. That means the last one goes at index 10. And we stick the 7 there. 4. We go to index 4. Yeah.
Why don't you just do all one, place all the 2s and then all the 7s and then place all the...
Okay, so tell me exactly what you want me to do.
So it looks like you're probably going to make several passes through that top array, right?
Well, I'm just making one pass, left to right. But I think what you're saying is, let's go back to the beginning. Because I get this question a lot. Why do this mess? We know that there are, in fact, if we could go, imagine if we went back to our original count array. It says there, so back to back to the way that array was before I did all that stuff. Why not do this? This says there are 2 zeros. Just go to our array and stick 2 zeros in it. And then stick in 1, 1 and 2 2s and no 3s and 1 4 and 2 5s. Why not do it that way? Why am I bothering with copying something down when this tells me exactly how many of each needs to go where? Yeah?
You'd have a double loop, because you'd have to say for each value in the spot 0 or whatever, right? So wouldn't it be a larger...
No, it's still be linear time. We do, as long as there are not a lot of zeros. And, you know, big long arrays with lots of zeros are problems either way, but it'd be perfectly efficient. That's not the problem. Yeah?
The index might refer to be like a struct, and there might be some
okay.
data.
So the deal is, you know, we've sort of abstracted away all the complexity. It may be that that what we actually have is we're sorting some big struct. He said, you know, the things we're sorting are, you know, are objects, and the integer is the key. And so we don't really have an array of integers. We have an array of objects containing keys. And so there you do need to physically, you can't just store numbers in here. You have to go copy a whole piece of data where it belongs. So just imagine this is just part of the thing that's being sorted. Yeah?
The other trick is, couldn't you have a really long piece of data, couldn't you do the modulus and then...
Yeah, where you're sort of anticipating where I'm headed. Okay? So in other words, if we really were just sorting small integers, we could do it the way I said. But just imagine that there's other data going along for the ride with the key. Yeah?
Why does it matter that we start from the right? Can we do the same thing?
Why am I going right to left instead of left to right? You must be thinking there's some reason, because why would I do it otherwise? Yeah?
Because you have that less than or equal condition on your count array, you want to make sure that you are getting the getting it in the rightmost possible place, because otherwise you could run out of room from the.
But exactly the same trick would work. If I went left to right, you know, when I hit like 0, it would say the last 0 goes, there are 2 zeros, the last one goes at index 1. I'd stick the 0 there. It would work just the same.
But then if you found like a 1 before you found your second 0.
No, it would say put it at index 2, so the 1 would go there. It really doesn't matter, you know, the question I guess is, does it matter what order, whether you go through it left or right or right to left? Yes?
Does that have to do with keeping the sort stable?
Yes, that's the whole thing. Turns out we need the sort to be stable. So that means that if there is, let's see what there are 2 of up there. Okay, there's that 2 at index 11, and there's that 2 at index 1. I want the last 2 to come after the first 2 down here. Imagine if that's a red 2 and that's a blue 2. I want the blue 2 to come first, followed by the red 2. So the order in which indexes that have the same value, numbers that have the same value appear up there has to be the same down here. And again, that doesn't make any sense whatsoever if the whole thing we're sorting is the integer. But imagine the integer has other data attached to it. We want the sort to be stable, and you'll see why in a minute. We don't want them to be, the relative order of the tied elements to be flipped down here. Yeah?
So why is this not like a fundamental sorting algorithm that we've learned from the very beginning?
Okay.
Is it because of the space complexity?
Well, no, it's going to turn out to be linear in space and time. So why is this the first many of you are hearing about it? Yeah?
Maybe because it only works on a specific data set?
Right, it's not general purpose. Right, it works for sorting things. See, we're having what property do the things that we're sorting have to have? You have to be able to use them as indexes into an array, for one thing. And furthermore, it turns out the order in which they need to be sorted has to correspond to the order that you get when you use them as indexes. So there are lots of things you can sort with these things, but there are lots of things that you can't. And it's not just, you have to use regular sorting algorithms, all you have to come up with is a comparison algorithm, comparison function. It's a little easier here. All right, so go through it again. We want to stick the 2 in the correct spot. That spot is index 4. We put it there. And notice the next 2 will go to the left, so it's stable. Okay? There's the 7. It goes at index 10. We put it there. There's the 4. It goes at index 5. We put it there. There's the 6. Index 10, or rather index 9. We put it there. At some point, yeah, I don't animate the whole thing. So the complexity of this thing, if you're sorting an n-element array, and m is your largest integer, is O of n plus m. This counting sort. So where's the n come from in the complexity? Yeah?
Iterating in reverse over the whole.
Right. Several times we make a pass through the array. Once to count it, and then once to do the sort. And where does the m come from? Yeah?
You need an n-length counting array?
Right. These counts, we iterate through the count several times too, and that's got to be lengthy. We've got to allocate it, fill it with zeros, and we've got to go make a pass through and add numbers together. Yeah?
How do you know what n is before you start?
Well, if we're doing, we would have to make a pass through the data array and find out what the largest integer is before we allocate this. So clearly, this is terrible if m is giant compared to n. I mean, imagine trying to sort a 1-element array that contains 1 billion. Okay? It'd just be a disaster because you spend all your time allocating that huge count. So we're not going to use counting sort in this pure form. We're going to use it in a different sense. Okay. So we're going to use counting sort as a piece of Radix Sort. So here's what we're going to do. We start with an array of non-negative integers again. Okay? What we do is we sort them using counting sort, but only by the low order digit. Okay, so we extract the low order digit and use that as the key. And then rearrange the array and get this. So we could do the exact procedure we saw on the previous slide, But when it comes time to actually take an element and figure out where it goes, you take an element, you get the last digit, use that as an index into your count array. And then you copy the entire thing, including the high order digit, into the new array. So when we sort that array up there, you count sort, just looking at the last digit, you get this. Okay, so you get the numbers that end with 0, the ones that end with 1, the ones that end with 2, and so on. So they're sorted by their last digit. Now, how can you look at that and tell that the sort at least has a chance of, let's talk about stability. What's a clue that the sort was stable? Yeah?
You start with the lower order digit and then do the
Well, no, just this single step right here. How can you look at this array and that array and say, yeah, it looks like the sort was stable? Yeah?
No, never mind.
Yep.
The 7 comes before 47.
Okay, so 0, 7 was to the left of 47 up there, and it's still true down here. The relative order of tied things is preserved. Similarly, let's see, there's 52 and 22. 52 comes first. It does up there as well. 16 and 26. 16 came before 26 up there. It does here as well. If we had done the counting sort left to right, they would have all been flipped.
Is that a bad thing?
Well, he said, is that a bad thing? This is the second step. Second step is you do another counting sort pass, this time starting from this array and looking at the high order digit. So now things are arranged. You get the things that start with a 0 come first. Then you get the ones that start with a 1 next, and then the ones that start with a 2 next, and so on. But in addition, it's totally sorted. How did that happen? How does sorting by the low order digit and then sorting by the high order digit achieve that? Achieve a complete sort? Yeah?
The low order digit is like a tiebreaker from the high order digits.
Yeah. The low order digit serves as a tiebreaker. So because the sort is stable, this is where stability becomes important. Okay, of course, sorting by high order digit is going to put all your leading zeros and then all your leading ones. But how did the order right here of all the things that start with a 2, how was that determined? Yeah?
It was preserved from the stability.
It was preserved from up here. It's a stable sort. Up here, the 1, the 21 came before the 22, which came before the 26, because we sorted by low order digit. Since it's stable, when we clump all the leading 2's together, it preserves the order from this array. Yeah?
So can we do away with stability and just sort first by higher order digit, then by lower order digit?
Sort first by high order and then by low order?
Yeah.
Well, what would we get if we sorted first by high order and then by low order? What number would come first?
I meant like slice short a chunk of the array with just low order.
Oh, you mean sort by high order and then sort the chunks individually?
Yeah.
Yeah, but that's kind of complex. This is a lot simpler. Just make 2 sorting passes. You don't, this. In your case, the second sorting pass is going to be, you've got to scan, find out the clump, and then sort the clump, and then find another clump. This is just 2 passes. Yeah.
Do all the values have to be the same magnitude? Like if we threw 100 in there with all these
Okay.
2-digit values, would it still work?
Right. So what if we had a 3-digit value? Yeah.
Would you have to do just 3?
Well, we have to do 3 passes if following this strategy.
So instead of being M size, now it's just the number of digit size.
Right. So if we follow this, this is the exact. We're going to improve on this slightly. But yeah, if we're sorting by digit, if you have your digits or if your numbers have up to k digits, it would take k passes. Okay. Each pass would sort on an increasingly more significant digit. But your counting array would only have to be of length 10. Yeah.
This is kind of off topic, but with algorithms that only work when there are no negative numbers, why can't we just add a constant to everything so that everything is not negative?
Yeah, so he's saying, what if we want to sort negative numbers? One approach, as he suggested, is we can add a constant to all the numbers to make them all positive if we don't have to worry about overflow, which you really do. do the sort and then do the subtraction. Another thing would be to, well, what would happen? Forget about overflow and underflow. Let me defer that question. Yeah.
Never mind, you deferred.
Okay. Remind me, I don't want to completely ignore it. That will be easier to talk about in a second. Okay. Here's what we're really going to do. It's expensive to get digits out of a number. You know, we have to do like mod 10 and such. So pulling digits out of a number represented in binary, pulling decimal digits out of a binary number is expensive. Let's not do that. Instead, let's say we're sorting 32-bit integers. Sort by the byte. So the first pass you sort by the low 8 bits. So our counting array has to be 256, which is certainly manageable. Then sort by the next highest byte, then the next highest byte, then the highest byte. When you're done, it'll be sorted. It takes 4 passes, you can sort an array of 32-bit numbers.
So is that just a shift and mask then?
That's just shifting and masking, yeah. It's, yeah, much cheaper than pulling out digits. It's equal, if I'm demoing to you, you know, you're all good at looking at, you know, you're good at looking at a decimal number and pulling out digits, but you're probably not so good at looking at a binary number and pulling out decimal digits. Okay? Computer's great at pulling out bytes, so we'll sort by the byte, just 4 passes. Now, let's go back to the thing I deferred. What if we threw in some negative numbers? Yeah.
Could you deal with that with 2's complement?
Well, 2's complement has to deal with it. Okay? What would the result be? What would the array look like when we sorted it? Yeah.
Sorry, if it takes too much time, you can just pass this, but how is a negative number, could you remind me how a negative number is represented?
Okay, negative numbers are represented in 2's complement, so you take the positive version of the number, complement all the bits, and add 1.
Okay.
Okay? So what property do negative numbers have? What bit do they start with?
1.
Start with 1. So when you're sorting by low order byte, next byte, high order byte, where will all the negative numbers end up if you do radix sort on an array of negative integers, of positive and negative integers?
Right side of the array.
At the end, right? So you'll have all the positive numbers in ascending order, because they all have a leading bit of 0. Then you'll have all the negative numbers at the end. In what order will they be going in? Okay, so the last one, what will the negative 1 is all ones. So it would, if there's a negative 1, it would be at the very end of the array. So you go from 0 up toward max int, and then you go from negative max int up to negative 1. So if you wanted to sort an array like that, what could you do? Yeah?
So you could just splice it where they
Yeah.
kind of start with 1 and...
You don't have to, you just sort it, and then you go find the negative number chunk, and, well, you couldn't just stick it at the beginning, you would have to... No, that would work, yeah. You'd have to copy it, you'd have to swap the 2 blocks, so it would take an extra pass to do it. Yeah?
Could you just separate them into different arrays to begin with, and then just
You could. You could make a pass and put them in separate arrays and sort them, put them back. What if you wanted to sort floating point numbers?
Oh, they're already, or, except for the...
Yeah, it turns out, you know, think of a floating point number. It consists of a leading sign, which is, you know, negative or positive, and then it has an exponent, which can be a positive or negative exponent, and then it has a mantissa. But the IEEE standard is defined so that if you ignore the leading sign bit, you can just sort them like they're integers. You can take, ignore, if you know, say they're all positive, you can just sort them like they're integers, and you're sorting them as floating point numbers as well. So Radix Sort works there as well, and you can deal with the leading sign bit the same way we do with integers. You just have to deal separately with the positive ones and negative ones. So there are lots of things you can sort with Radix Sort. Yeah?
So is there a reason why we do it in 4 passes instead of 2 passes? Is it because
Okay.
we cache block it or something?
He's asking, why do it in 4 passes? Why not use 2 passes?
It could be 16, so that's just a...
Right, so instead of using a 256 element array, we would use a 16,000 element array, 2 to the 16th. No good reason. I mean, I guess there is a good reason. It's just how big of a counting array do you want to allocate? Yeah?
This is slightly low level, but that wouldn't fit the cache.
Okay, so yeah, he did say something about caching up here.
Yeah.
And that reminds me of, I don't know how long ago, probably 10 years ago, I ran a little contest in this class. And I said, I want to see who can implement the fastest Radix sort. And so, you know, we got some fast ones, but one was noticeably faster than the others. And so I sat down and I spent like an hour looking at it. I finally figured out the student had done something really clever to exploit caching. They were doing things in a different order than other people have, and it just turned out that as a result, the cache sped his thing up. And so in class, I like pointed this out, and I asked the student who had done it, you know, how hard it was to come up with this idea. He says, he was like very embarrassed. It's just luck. He hadn't designed it. It just worked out that way.
So if it's cache block, wouldn't it depend on your machine as well? Like,
Yeah, so if you're depending on cache effects to speed it up, yeah, it's going to depend on the machine and how big the cache is and all that stuff. Anyway, I mean, we're talking about 2 passes versus 4 passes. You could say, okay, we'll do 2 passes, and our array, our counting array has to be, you know, have to have 2 to the 16 spaces, which is about 64,000. But that wouldn't, you know, that's not bad if you're sorting a million-element array. If you're sorting a 10-element array, that's a big price to pay. So bytes just seem like a good compromise to me. Okay, so that we got that. So each pass, there are only 4 passes. Each one is n, O of n, plus the 256 overhead, which is a constant. So it's, for sorting fixed length integers, it's linear time. And it's, if you time it, it's going to be faster than quicksort for large arrays. Now, what happens if you're sorting big integers, k-byte arrays, k-byte integers? What's the complexity going to be? So arbitrary length, but we'll let k be the maximum number of bytes of the largest integer. So k is a variable, yeah.
3 times n then?
Right, it's going to be k passes, each a complexity n. So it's O of kn. All right, so what can you say about that? Yeah?
Well, for the magnitude of k, that would be log of k. So this is the same as like quicksort,
Well, let's think about it.
or no?
Would you call that linear? It is linear. What is this? How many bits are in the array you're sorting? Or how many k is bytes? How many bytes are in the array you're sorting? K times n. There's k bytes per number, and they're n numbers, so there's k n bytes. This runtime is proportional to the size of the array. That's the definition of linear. What would happen if you quicksorted such a thing? Would it be O of n? I mean, O of n log n in the average case. Okay? What assumption do we make when we analyze algorithms like, what assumptions have we made in the past when we've analyzed algorithms like quicksort, sorting algorithms? What have you assumed about comparisons?
Constant.
That they're constant time. But comparisons aren't constant time when you're sorting arbitrary length integers. In the worst case, you've got to look at every bit to do a comparison. So in that case, since quicksort does n log n comparisons, O of n log n comparisons, the actual cost, each comparison is going to be O of k in the worst case. You get k n log n. You multiply the number of comparisons by the cost of the comparison. In the worst case, quicksort would be k n squared. Yeah?
I'm just a little confused on 4 passes for each byte. So
One pass per
byte. 1 pass per byte. So are you using the byte similar to decimals where you're using the low order number? But in this case, it's just the lower byte, not the bit?
Yeah. Instead of pulling digits out and using them to do the counting, we pull a byte out. We view the byte as a number from 0 to 255. And we do counting sort, like I showed you, on an array of length 256.
So it's still represented as a decimal number after.
Well, it's just we're sorting binary numbers. You know, I use decimals to start with because we're all good at decimals. We don't have to think twice to pull out the low order digit and the high order digit. But when actually use it in practice, it'd be unnecessarily expensive to pull out digits. We just pull out bytes, which are just small numbers. Yeah?
Just why not just take out the bits?
Well, you mean like one bit at a time? Okay. What would Radix Sort look like if we pulled out the low order bit and then the next bit and then the next bit?
Sorting.
We would have a tiny little counting array of length 2. But it would just take 32 passes instead of 4. That's not a very good trade-off. In reality, what you would do, I think, is do some timing experiments and figure out the optimal number of bits to pull out. But I think a byte's probably pretty good start. Any other questions? Okay. So what that does for us now is, this is our analysis again of Kruskal's algorithm. And this used to be the O of E log E term. Now it's just O of E if we use Radix Sort. We can sort E edges in O of E time. And so that just leaves this stuff, which since the graph is connected, simplifies to that. Where does this come from? The log V come from?
Oh, it's our directed tree. It's,
Yeah, that's our disjoint set data structure. Yeah. So now we're back. If we want to improve this anymore, we got to improve the disjoint set data structure. Okay? Well, let's see how to do that. Okay, we already had a preview of this when we talked about the disjoint set data structure, which was, that was your idea, right? Which was, when you're doing a find, it's possible to optimize a tree a little bit. And let's just remind you what that was. Suppose we're doing a find on, let's see where I am. No, that's weird. That's an artifact of converting over from PowerPoint. Anyway, let's start here. Okay, we're doing a find on H. So we're going to, okay, now we start at H. Wow. Go to G. Sorry about this. I think I know what's happening. I won't try to explain it. We go to F. We go to C. Okay, so if we ignore those edges disappearing and appearing, we end up at C in the find. Now, imagine we now exit the way we came in. We walk backwards down that chain. Maybe we remember the path that we took. As we go out, we go back to F, and we make F point to C. We go back to G, we make G point to C. We go back to H, and we take that pointer from, this is awful, I'm sorry. Okay, that's the end effect. So originally, H pointed to G, G pointed to F, F pointed to C. So we found out that the root of that tree was C, and so we just arranged for F, G, and H to all point to C at the end. So we walk the list in one direction, we find the root, and then as we go back, we just hard code, we just make every one of these nodes point to the root directly. That makes the tree shallower. It's going to make future finds faster.
Doesn't it have a cost of log V though to do that?
A cost of log V? We're already doing the find though. Okay? So we're using this data structure. The find has been called. We've got to go all the way from the leaf to the root. While we're at it, we might as well modify our tree a little bit so that it's shallower. So we're not adding any extra operations. We're making find a little less efficient. Before you walked all the way to the root, and then you were done. Now you've got to walk back and adjust the pointers. Yeah?
Are we supposed to be like updating the weights of the nodes?
Okay, so he asked, at this point, it's no longer true. You know, F is not rank 2. F should be rank 1 now, and C should be rank 2. But that's too expensive to figure out. Because we didn't even touch, well, we did touch F. But in general, you can't tell what F's rank is supposed to be now unless we go look at all of its children, which is hard. So we give up on that. We just, instead of saying that the rank is the depth, we say the rank is an upper bound on the depth. And really, the only ranks that matter are the ones that are at root nodes. Okay? So that's our optimization. And like I observed, this flattens a tree, leading to improved performance. So here's our original find operation. It started at x, it just said while x is not its own parent, x becomes parent. So that's how you walk from the leaf to the root. Okay? Let's make it recursive. If x, so find of x says if x is not equal to the parent, do a find on parent of x and return it.
So you're just using that.
All right, so we just basically a sort of a reverse tail recursion optimization. We're taking the iterative thing and turning it to recursion. Recursion is not so bad now because the trees are shallow and we're making them shallower. Once you have it in that form, then you can do the path compression. So there's our recursive version of find, and we just have to change it so rather than saying x equals find the parent of x, we say parent of x equals find the parent of x, and then we return parent of x. So all we're changing is this x that we're returning, we also store it in parent of x. So with a constant amount of overhead, we can compress the data structure. Now, I think that there's an analysis, a detailed analysis in the book of the complexity of when you do path compression, the complexity of a find operation when you do path compression. I think it is the most involved complexity analysis in the whole book. So I'm not going to try to repeat it here. I'll just tell you the answer. So the result is if you do a sequence of M operations, union find operations, you can, so it's an amortized analysis. We're just saying that a sequence of M operations will take M times log star of N time. What bound did we have before? M log N. So we replace log N with log star N. Now you may be wondering, I'd be surprised if most of you aren't, what is log star of N? It's called the iterated logarithm, and I'll just give you the idea. It's the number of log operations required to cut some number down to 1. So log star of 1 is 0, right? You don't have to take the log of 1 anytime to get 1 as an answer. Log star of 2 would be 1. You take, talk about log base 2. Log base 2 of 2 is 1. What would have a log star of 2? Not 4. Yeah, you're right, 4. I got ahead of myself. Okay, log of 4 is 2, log of 2 is 1, so it took 2. Now, what would have a log star of 3? 16. Log of 16 is 4, and then so on. That number there, 2 to the 16th, has a log star of 4. That number there has a log star of 5. And there, it just doesn't matter what comes next. So the details aren't important here. Another way to think about it is, imagine if you wrote a number as 2 to the 2 to the 2 to the 2 to the 2. Log star measures how high that stack has to be. So repeated squaring. How many times you have to square something before you get to that number? Yeah?
So if we wanted to just cement this in our minds, we could just say if we've got log star of some linear thing, it's just less than 5.
Yeah, that's a good rule of thumb is, you never, I mean, 2 to the 100 is a huge number. It is an unimaginably huge number. That's just beyond the realm. So for all practical purposes, log star is a constant. Yeah.
Yeah, sorry, so why don't we even view that as O and not just no, like, reason why would we consider a number that is 6?
Yeah, so we could, with a lot of justification, anytime you see a log star, you just replace it with 5. Okay? So what that means is, in the final analysis, we got our algorithm takes E log square of V time. For all practical purposes, that's O of E. Unless you're, a real stickler. I mean, technically, it's not, but in reality, it might as well be. Okay?
So how did this compare to Prims? Prims was V log V?
Prims ended up being the same as Dijkstra's. Dijkstra's is E plus V log V because in Dijkstra's we didn't assume that the graph was connected. If you assume the graph is connected, prims and Dijkstra's both end up being E log V. So the difference between prims and Kruskal's is one is E log V, one is E log star V. And in reality, log V is pretty small too, unless you're talking about really large graphs. The only place you'd see a difference. Yeah?
So you care about this if you're doing like an MST of the internet or something. But outside of that, it's kind of like, they're pretty much the same?
Yeah, I think Kruskal's is going to be faster
Okay.
for really large graphs.
Is this true like in practice? Like are there like high order?
Yeah, really, I'm not sure really what, I said that, and I'm confident that if the graph is large enough, what I said would be true. What I don't know is how large the graph would have to be.
So is there like a blended version of Kruskal's?
Well, he's asking, is there a blended version of Kruskal's? The problem is, Kruskal's isn't a divide and conquer algorithm, so it's not obvious how you would, how you would switch over at some point. Wow. So I've had proofreading mistakes get through when I did these conversions for PowerPoint. But obviously, I didn't proofread those slides at all. What happened was the PowerPoint slides have animations each. Typically, I might have 10 slides in PowerPoint, end up with like 150 in Google Slides because the animations turn into multiple slides. And what I did was I created the multiple slides, but I left the animations in. So it was sort of animating both ways, if that makes any sense. It was sort of a double animation. I know how to fix it though. Let's take a break and look at something completely different. get us started again. All right, so I woke up this morning and it was cold and it was snowing and my wife was out of the house and the cat was screaming to be fed. But within a few seconds I had a smile on my face because I knew that starting today I get to talk about dynamic programming.
Can I make a comment?
Yes?
Stephen Hawking died today.
Yesterday.
Yesterday. Okay, well, I should say he died. I don't know if everyone knew, so.
And also Einstein's birthday yesterday too.
Okay. So I like dynamic programming. It's unfortunate that spring break usually comes in the winter. This year they put it in spring, and it's almost in spring. And so spring break is splitting our discussion of dynamic programming, which is unfortunate. We'll sort of have to start over after spring break. But anyway, we'll get a start here. The caddis problem on the assignment due after spring break is a dynamic programming problem. And I just want to point something out. There is the caddis problem. There's also a written problem, a regular problem on the assignment, where you do the design work that you use for the caddis problem. So there's sort of, I give you help in the regular problem about how to approach designing the solution. So do that first. Right? Do the design problem first, then take your design and implement it, and try to do it the other way around.
So
it's easy to overlook, yeah.
So we don't do caddis first and then come?
Well, you can do it in either order, but I'm just saying it makes sense to. I don't remember exactly how my written problem is worded, but I think it leads you a little bit through the design of the solution. Whereas if you do the caddis problem, you're sort of starting at it cold. So here's a simple problem we're going to solve with dynamic programming. Imagine you have a steel rod that's N meters long, and you're in the business of selling steel rods. And there's a sort of a price table that says, okay, a 2-meter rod can be sold for this amount, a 4-meter rod for this amount. And so the question comes, how should you cut you're going to cut the rod up into pieces and sell the pieces. What pieces should you cut it up in to maximize profits? Now, you're thinking in a rational world, it really wouldn't matter that, a 1-meter rod would cost about half what a 2-meter rod costs. But let's just assume that's not the case. And so let's take this for example. Say you have a 6-meter rod. This is saying that a rod of length 0, isn't worth anything. A rod of length 1 you can sell for $1. A rod of length 2 you can sell for $2. But a 3-meter rod you can sell for $4. So that, owned up to $7 for a 6-meter rod. So the question, this is an optimization problem. You've got to, essentially, the choices are, you've got a rod, you've got to cut it somewhere. And after you've cut it, you've got to cut it somewhere else until you decide not to cut it anymore. You've got to decide what cuts to make to maximize. Now we could make it more involved. We could say each cut costs you something. Maybe it costs 50 cents to cut the rod. And that would make the problem a little more complicated. But we're just trying to make this as simple as possible for our first dynamic programming problem. So that's not too hard to solve in your head. What would be the optimal way to cut this rod up to maximize your profits? Yeah, you cut it in half and sell each piece for $4. So this is the 3-meter chunk you can sell for $4. That's better than selling the whole thing. It's better than cutting a 5-meter piece and then 2 1-meter pieces. That would only give you 7. Right? Now, first thing you ought to think, is there a greedy algorithm that we could use? That would be the ideal. A greedy algorithm that could do a quick computation and say, cut here. Okay? I'll save you some time. No one knows such an algorithm. This problem is, you could cast it as a version of the knapsack problem we talked about before. But basically, in the general case, no one's ever found a reliable way, a correct way to always make the greedy choice. So what we're left with is trying all the possibilities. Just systematically consider all possible cuts you could make. See which one is best. Okay? Well, let's see how well that works. Here's a solution that tries all the possibilities. So there's our main method. It takes in a list of values. an array of values, and all it's doing is calling this helper method. And the helper method is, you've got a rod of this length. Starts out, the initial call is to be the maximum length, like 6 or whatever it was. This is the table, and it figures out the maximum profit. And the way it does it, it says, okay, let's let max profit be 0. And then it iterates through here, and it starts looking at, it considers all possible places to cut the rod. So it has a rod of a given length. It considers cutting it at n minus I for all these values of I. So what if we cut it what if we cut it at position 0? We'd be saying, okay, what's the best you can do with a rod of length 0? Then we'd say, and then we would iterate and say, what's the best you can do with a rod of length 1, and then a rod of length 2. So what it does, for every possible place to cut it, it figures out what the cutoff piece is worth, and it adds it. It makes this recursive call to figure out how much the rest of the rod is worth. And that will involve cutting it up some more. It's just a maximization loop, so it's finding the best you can do for that first cut. And it returns the max profit. So it's recursive, but and this is just the way you systematically try all the possibilities. Given a rod, try every possible place to cut it, see how well you do for each cut, return the maximum, and the way you find out what a cut is worth is you cut off a piece and figure out what it's worth. You recursively figure out what you can do with the piece that's left. All right, so dynamic programming is just involves recursion. Right? You have to be able to think recursively to deal with dynamic programming. Well, what do you think of this solution?
Expensive.
Why is it expensive?
You're making recursive calls that iterate.
Okay, so you've got this iteration inside a recursion. So let's say you start with, say that n is 30. How many recursive calls are you making? 30. Okay, each of those 30 is going to make some recursive calls. Okay, one of those recursive calls is dealing with a 29-meter rod. How many recursive calls is it making? 29. One's dealing with a 28-meter rod. 28. 27. And then this 29 one is going to be making recursive calls for 28-meter rod, 27. It adds up fast. It's bad.
Where's it back, bro?
Yeah, this is awful. But it's correct. If you ran this and waited long enough, if you had long enough, you would get your answer back. Now, in fact, I can show you the timing in a bit. Well, it depends on how long it takes for other things. So the deal with dynamic programming is, the way it works is you take a problem, you realize you can't use a greedy algorithm, you write a recursive solution to solve it, and then you improve the recursive solution. Let me show you how you can improve this. All right, this is the derivation of the complexity, and I'm not going to go into details. But the time it takes to deal with a rod of length n is the time it takes to deal with an n-1 meter rod and n-2 all the way down to 0, plus linear time to account for the loops. So you've got a loop, that's the n, and then you're making all these recursive calls. And, you know, that's greater than or equal to t of n-2 plus t of n-2. This is bigger than that, this is the same as that, and theta n's are the same. So we're just throwing away a lot of the recursions. We get that. Like I say, I don't want to belabor the details, but we end up with a constant to the nth power, square root of 2 to the nth power. So it's exponential. It's enough to know that it's exponential. Now, let's look at what recursive calls are happening. So RP30, RP is our recursive method. It's going to, it's going to call RP of 29, of 28, of 27 down to 0. So it's making all those recursive calls. RP of 29 calls RP of 28, 27, 26, and so on. RP of 28 calls all those. What do you notice? Yes?
If you work backwards, then you don't have to
call.
All right, so he's saying if you work backwards, you don't have to know those calls. That's one way of putting it. What's another thing you notice? Yeah?
There's a lot of repeat work.
A lot of repeat work. How many unique ways are there to call? How many different calls to RP are going to be made in terms of the parameter?
31.
30. 31, yeah. RP of 30 is called, RP of 29 all the way down to RP of 0. So where does the exponential come from? It seems like you're just making 31 calls. Yeah?
We never save our result, so we're just recalculating every single time.
Okay. So that, yes, there are an exponential number of calls. That's because we're calling some of these, for some of these parameters, we're calling them an exponential number of times. It isn't that there are lots of things that have to be solved, it's that we're solving them over and over and over again. Yeah?
So can we just cache it in our function?
Right. The idea is compute it once. Save the answer. Next time, look it up. That's the whole idea of dynamic programming. Is you create a recursive solution, you observe, you know, yeah, this is exponential, but it's only exponential. They're only a polynomial number of different problems. So you cache them. So RP29 is called once up there. RP28 is called twice. RP27 is called 4 times, 8 times, and so on. That's where the exponential comes from. And so on. So this is, when you see that, a recursive solution, and that's just wasting its time solving the same problems over and over again. Sometimes you have a recursive solution, and each recursive call is unique. You have an exponential number of recursive calls, and they're all different. That's not what dynamic programming can solve. So here's a solution. So I've modified my method. The differences are highlighted in yellow. So now the top level method calls, passes in an empty hash table. So we're passing a hash table around. You can also make that a global variable. When we enter the method, first thing we do is we find out, have we previously computed the result for n? We ask so the dictionary is going to store solutions for different values of n. So we say, okay, have we solved the problem for a rod length of n? If we have, we just return it. So it's constant time. We look up the answer. If it's been saved previously, we return it. Otherwise, we do what we did before. You know, that's different because we changed the name of the method. We're calling this thing recursively. And then at the end, we take the number we compute, we store it in our cache, and return as usual. So the method has, you know, works the same way, except it gets shortcutted every now and then. We do this so that if in the future it's called with the same value then, we can just look up the answer. Very easy to do. This is where the dynamic programming comes from. Dynamic programming refers to this idea of there are different ways to do the caching, but essentially to figure out a way to do the problem so you can cache the answers. So the name is misleading. When you hear dynamic programming, you probably think, you know, dynamic memory or something, but it's an old term, you know, probably from, you know, middle of the last century. So, right. Now, what's the complexity of this solution? Let's see. DRP of n is going to call each of those things one time only. So that takes time proportional to n minus 1. DRP of n minus 1, when it has to get computed, it's going to call all those things one time only. Time proportional to n minus 2 and so on. But, so it's n squared. We've eliminated an exponential number of recursions. Now, I just want to show you the difference this makes in practice. So here is our program. There's some timing code. Let me just get down to and it creates a random array. So there's our rod profit method, just like I showed you on the slide. That's the pure recursive rod profit method. And here is dynamic rod profit, just like from the slides. It has the cache. All right? Up here, I time rod profit, and I time dynamic rod profit. And this delegate parameter right here is just to control what values of n I use. So this one uses value, we time rod profit with a 20, with n being 20, and then 21 and 22 and so on. With dynamic rod profit, we start at 20, but we double it each time. Double n each time. Big difference. So let's run it and see what happens. So this is regular rod profit. So you see that we increase n by 1, the running time doubles. That's exponential. Oh, while my back was turned, it did dynamic rod profit. 20, 40, 80, 160, 50, 120. And you notice we double the size, it quadruples roughly. So that's an n squared algorithm. So you see n, whatever that is, we dealt with 5, 120. Dealing with 28 took 3.5 seconds up there in the pure recursive version. Yeah?
I think that you can actually make that other one faster too, because you're passing the dictionary by values as having a copy at a recursion.
Sure. Yeah, we can improve the constant. We could take the dictionary and just make the dictionary a static variable or something, so we don't have to pass it.
Yep. The difference.
Yeah. So, I mean, the difference is just astounding. I mean, that's the difference between exponential and polynomial. Quadratic in this case. Now, if you think about it a little longer, you don't even need to use recursion. Who could think of a way to do it non-recursively? Someone did earlier. What would be the... We're solving the problem by starting with, say, 30 and working down. What if we solve the problem in the other direction? Suppose we just create our cache. It could even be an array indexed by the size of the problem. And we solve it for 0. Then we solve it for 1, which involves iterating over the number smaller than 1. So we're basically filling in a table from the bottom. We solve it for 0, for 1, for 2, for 3, for 4, all the way back to 30. We never have to make a recursive call, because when we have to compute rod profit of 30, we just consider all the possibilities. So we got to iterate through the table. We don't have to make a recursive call. So that's sort of the end game of dynamic programming. Sometimes, or in fact a lot of times, you can get rid of the cache and change the order in which things are computed and get rid of the recursion. But the key step is to reduce it from exponential to polynomial time. Yeah.
Is that a property of a problem that can be solved by dynamic programming? Like that you could change it to a bottom-up approach?
Yes.
Okay.
So I've done it both ways in the past. I have done dynamic programming by starting by saying, look, it's just a matter of filling in a table in the right order. The problem students have with, and I have sometimes as well, is to figure out what order to fill the table in. So it's simpler to say, write it recursively, then cache it, and then if you want to go a little bit further, you can contrive to turn it into filling in a table instead of doing it bottom up instead of top down. But it won't improve on the n squared. It just gets rid of a constant.
Yeah, wouldn't you require like linear recursive calls? Couldn't that just blow up the stack easily?
True. So think about the depth of recursion here. If you start at 30 and recurse down, you got 30 stack frames. This one has 5,120 stack frames when it recurses from the high level to the bottom level. So that is the reason you would get rid of the recursion and the caching this way. And instead, if you want to compute rod profit of 30, start with computing it for 0, then for 1, then for 2. Fill in a table iteratively, and then you don't worry about blowing the stack.
Like space efficiency is
right.
The main motivation.
Right, so it's space efficiency. So I'm sort of getting ahead of myself here, because what I've got to get you comfortable with first is taking a problem and if you can, the problem is figuring out the recursive algorithm to use to compute the answer. That causes students trouble. Once you can do that, it's caching the answers, or like, it's simple. There's no thought required. You just look up the answer on the way in and cache it on the way out. So the creative part, the hard part, is coming up with the recursive solution in the first place. So let's see. what we can do in 10 minutes. Okay, so we're there. And this is just what I've been saying all along, so you can go review that. All right, here we're going to talk about another problem, the longest increasing subsequence problem. So what we want to know is, given an array of integers like that, what is the length of the subsequence of that list that increases as you go from left to right? So for example, 5, 7 is a subsequence of that whole thing, right? 5 come, you throw away some of the numbers, you got 5, 7 left.
5, 6, 7.
Well, 5, 7 is still a subsequence.
Okay.
And that's of length 2. 5, 6, 7 is a subsequence. That's a better one. The question is, what is the longest subsequence, the longest increasing subsequence you could make? You want to throw numbers out, and you're left with numbers that increase, strictly increase left to right. Who's got it? Yeah?
2369?
2369 or 2367. So the answer would be 4. The longest increasing subsequence has length 4. That's what we want to compute here. All right, so there's a solution. Yeah. No one knows a greedy algorithm for doing that. So key idea. So the key idea is what you come up with. Define longest of I such that, which returns the length of the longest increasing subsequence that starts at index I. So conceiving of the recursive method you want to define, that's often the crux. So I took a problem that takes an array as a parameter, and now I'm viewing the array as being a global variable now, but what I conceived was that what I needed to define was I need to have subproblems. I need to be able to create subproblems. So longest of I is the length of the longest increasing subsequence that starts at index I. So what would be, up here, what would be longest of 0? It would be 5, 5, 6, 7, or 5, 6, 9, or 5, yeah. So it would be 3. What would be longest of 1?
2, 3, 6, 9.
2, 3, 6, 9, or 2, 3, 6, 7. So you're basically saying it has to start at I. What's the best you can do if you're constrained to start at I? Right? So let's see how we can do that. How can we define longest I? Well, here is my definition of longest of I. Okay, the best you can do if you start as I. Well, let me back up. I don't want to freak you out. Let's try to explain it without looking at the math. What's the best you can do if you have to start at index 3? What does trying all the possibilities mean? So we want to try all the possibilities if we start at 3. So we know we start with, in this case we're using letters instead of numbers, so we want to increase output of the word. F will be first. We want to look at seeing, okay, what happens if we choose C, or what happens if we use F as our next one, what happens if we use J, what happens if we use E? Okay? Well, should we even consider using C as our next one? No, it's not. It's not increasing. We could use F as our next one, and no.
F's F.
We can't use C. We can't use F. We could consider J, basically. So not such a great choice. Let's do this one here. Okay? We could conceivably do B followed by H, or B followed by F, or B followed by C, or B followed by that F, and so on. So they're all possibilities. How do we figure out which one is best? Yeah?
Would you look at the longest subsequence
Right.
of everything else?
We compute longest of 2 and add 1 to it. That's one way we could solve the problem. We could start with the B, and then we see what's the best we can do if we start at index 2. Add 1 to it for the B, and that's our answer. We try all the possibilities. We find the solution to each of these subproblems, longest of 2, longest of 3, longest of 4, or 5, or 6, or 7. Take the largest of those, add 1 to it. That's the best we can do, starting at index 1. Yeah?
So we might want to go backwards then.
Well, yeah, so,
Right?
yeah, yeah. in the end, it works best to sort of compute it backwards, because you always want to compute the numbers that you need before you compute the numbers that need them. But, you know, I don't want to, let's not skip that. So that just takes what I said and puts it in a mathematical form. That says what we're doing is we are taking the max. We look at all j's bigger than I, and for each j, we compute longest of j if a sub I is less than a sub j, or our answer is 0 if, if a sub j is less than or equal to a sub I. We take the max over all the possibilities and add 1, and that's our answer. So obviously, there's a recursion there. Longest of I is defined in terms of longest of j. So, how do we turn that into code?
Initialize a 2D array?
Yeah. Well, let's look at the code here. That's rod cutting, and we need to do increasing subsequences. So here's our timing again. So here is longest SS. So longest SS gets an array A, and basically it says, okay, what's the best you can, it recursively determines the best you can do if your subsequence begins at index 0, if it begins at index 1, if it begins at index 2, and so on. So it calls this method for each possible starting point. It figures out the max and returns it. What's this method doing? This is the actual recursive method. So it's asked, what's the best you can do starting at index I? So it says, okay, my max length is 0. In the end, it's going to return max length plus 1. It considers starting, it's looking where to put its second element. At j plus 1, at I plus 1, at I plus 2 is I plus 3. So for each one where the letters are in the right order, it figures out the best it can do, makes a recursive call, figures out that's better than the old max length. In the end, it returns 1. It adds 1 and returns it. So that's the C# version of the math that I showed you. How do you memoize it? This is going to be exponential because it's solving the same subproblems over and over again. How do you memoize it to make it faster? This, memoizing it, if getting to this point is the hard part, memoizing it is the easy part. So what would it take to memorize this thing? So that we only compute it for a given I, we only compute the answer once. Yeah?
You save longest subsequence of j?
Well, how do we memorize the previous method? Yeah?
We have a dictionary that maps I to whatever.
Right. So we have a dictionary. On the way in, we looked up the answer to see if we had it. If we had it, we returned it. At the end, we cached the answer. So if you want to see how to memorize it, here is the method. Right here. It just takes a cache as a parameter. On the way in, it looks, have we solved the problem for I? Have we already figured out the length of the longest subsequence that starts at index I? If so, we return it. If not, we compute it and save it before we return it. And it turns an exponential algorithm again into a quadratic algorithm. Okay? Now, I know it's hard to learn something new in the last 5 minutes of class, or the last half hour of class, especially if it's the last half hour before spring break. So have a good spring break. We will probably back up a little bit and restart after spring break.